So, a rather scary looking integral over here. Can you calculate it using complex contour integration? So pause the video and sink your teeth in it. Right, this is an integral from 0 to 2 pi. So this means we're going to use the unit circle as a contour, and we're going to parameterize that unit circle by having z equal to exponential j theta. This means, of course, that dz is going to be j exponential j theta d theta, or jz d theta. So that's d theta taken care of. We still have the cosine to worry about, but we know that cosine of theta, that we can write this as exponential j theta plus exponential minus j theta divided by 2. And that, of course, we can now write as z plus 1 over z divided by 2 with our parameterization. There's a final ingredient missing, and that's the cosine of 2 theta. However, cosine of 2 theta, that's going to be exponential j 2 theta plus exponential minus j 2 theta divided by 2. And obviously we can see that exponential j 2 theta is nothing more and nothing less than exponential j theta squared, or z squared. So we get z squared plus 1 over z squared divided by 2. So this is how we reformulate our problem, getting rid of all the trigonometric functions and just writing it as polynomials. So now could be a good time to pause the video again and make all of these substitutions and see what happens to our complex integral. Okay, let's see what happens. Our integral is going to be an integral from 0 to 2 pi, so that's going to be translated by a contour integral over the unit circle. And then cosine squared, that's going to be z plus 1 over z squared. And then 1 over 2 squared, that's going to give us an extra factor of 1 over 4. So that's the numerator taken care of. For the denominator, we have 13 minus 5. And then we have the cosine of 2 theta. That's going to be z squared plus 1 over z squared divided by 2. And then finally, d theta is going to be dz divided by jz. So now we have all the ingredients plugged in, just a matter of simplifying this. It's not a difficult calculation, it's just slightly painful, let's say. So the first thing we're going to do is try and get rid of this 1 over z and 1 over z squared. So we're going to multiply both the numerator and the denominator by z squared in order to clean stuff up. So we're going to have an integral of this 1 over 4. Then for the numerator, after multiplication by z squared, or multiplication by z inside these brackets, because we take the square, this is going to become z squared plus 1. And then for the denominator, we have 13 z squared minus 5 over 2 z to the power of 4 minus 5 over 2, like that. Okay. So then we, of course, should not forget our dz divided by jz. So it's starting to clean up a little bit. What we're going to do now is from this factor 4, take out a factor 2 to get rid of that denominator 2 over there. So moving on, we have 1 over 2, and I forgot a square here, z squared plus 1 squared. Then we have 26 z squared minus 5 z to the power of 4 minus 5 dz jz. Now I'm going to bring that j to the numerator, which will give me an extra minus sign, which I can use to clean this thing up a little bit further here. So it's finally 1/2 z squared plus 1 squared. And then let's order things here so that we have 5 z to the power of 4 minus 26 z squared plus 5 1 over z. Good. So this looks already quite nice. The only thing we need to do now is sort of like factor this. Now this is a quadratic equation, not in z, but in z squared. So we can calculate the solutions to that equation. Moreover, here it turns out that our coefficient of this middle term here is an even number. So we can use the reduced formula here. So we have minus half of that number. That's going to be 13 plus or minus that 13 squared minus then the product of this guy and that guy. So that's going to be 25 and divided by the coefficient of this guy over here. So that's 5. So these are the reduced formulas you can use in case this is an even number. If you don't know those reduced formulas, just use the regular formulas, but then this becomes slightly more unwieldy. Let's have a look at this 13 squared minus 25. So that's going to be 144. So that's going to be 12 squared. So basically we have 13 plus or minus 12 divided by 5. It works out quite nicely. First of all, 13 plus 12 is 25. 25 over 5 is 5. 13 minus 12 is 1. So we have two solutions, 5 and 1 over 5. So let's take the final step here. Let's have an integral of z squared plus 1 squared. And then we have 2. We should not forget, of course, that we have a factor 5 here. So when we write that as a product, we should not forget about bringing this 5 to the front. So we have 5. And then we have solutions where z squared is either plus or minus 5. So where z squared is 5. So z will be plus or minus the square root of 5. And then we have another solution for z squared, which is 1 over 5. Then we have dz over z. And I forgot to bring the j to the numerator, which I also should have done here. So quick double check. This indeed seems to be correct. Good. So again, not a difficult calculation, but a bit painful. And this is what we have now. So this is a good intermediate checkpoint to pause the video again, because the next step we need to do is identify which of the zeros, which of the poles here are relevant, calculate the residues, and then we're done. Okay, welcome back. Let's take the final step here. Let's have a look at all the zeros that we have of the denominator, so all the poles that we have of the integrand. We have a 0 at the origin, which sounds good because that's lying inside the unit circle. We have another set of zeros plus or minus 1 over square root of 5. And then we have plus or minus the square root of 5. So these are our poles, plus or minus 1 over square root of 5. And then plus or minus square root of 5. Now these last two, of course, we don't need to consider those because they're lying outside of the unit circle, but these three are lying inside of the unit circle. So now let's calculate the residues. Let's start by calculating the residue at the origin. So in order to do that, we need to take our function and multiply that by z minus 0, and then evaluate that at the origin. So we have z squared plus 1 squared j divided by 10 z squared minus 5 z squared minus 1 over 5. And then that 1 over z here will cancel with the z minus 0 that we will have in the numerator. So evaluating that in the origin gives us j for the numerator. And then this becomes minus 5 times minus 1 over 5. So that just becomes unity. And then we have 10 in the denominator. So the residue at the origin is j over 10. Good. Next step is the residue in 1 over the square root of 5. So for that, we have z squared plus 1 squared j divided by 10 z squared minus 5. So z squared minus 1 over 5, we're going to factor that as z plus 1 over square root of 5 times z minus 1 over the square root of 5. Of course, we multiply in the numerator by z minus 1 over the square root of 5. So what we're left with is z plus 1 over the square root of 5. And then let's not forget, of course, that z, which is still present there. So this becomes the equation which we have to evaluate in 1 over the square root of 5. So let's get to work. Z squared, that becomes 1 over 5 plus 1. So that's going to be 6 over 5 squared j. Let's work on the denominator. That's going to be 10. We have 1 over 5 minus 5. And then we have, let's have a look here. So we have 1 over square root of 5 plus 1 over square root of 5. That's going to be 2 over the square root of 5. And then finally a z, again a 1 over the square root of 5. Right, let's continue. So that's going to be 36j divided by 25. And then for the denominator, we have 10. So we have 1/5 minus 5 is going to be minus 24 over 5. And then we have 2 over 5. Of course, the denominators here, that cancels. The 36 and the 24, we can divide those by 12. It's going to be 3j. And then we have 10 minus 2 and 2. So at the end of the day, we have minus 3j over 40. Okay, that's good news because we have this complicated calculation done to find the residue at 1 over square root of 5. Almost finished. Let's now see what happens for minus 1 over square root of 5. So we suspect that will be very similar. So let's see what happens. We have again z squared plus 1 squared j. Where do we have the sign changes? Okay, so far so good. Nothing changes. But here, rather than having z plus, we have z minus 1 over square root of 5. And then we have z. And also another change is we evaluate in minus 1 over square root of 5. So what changes here? So the numerator is the same thing because the minus sign, when we square it, that vanishes. So we have 6 over 5 squared j. And then for the denominator, again, we have 10. Again, this thing doesn't change. So we have 1 over 5 minus 5. Here things start to change a little bit. So we have minus 1 over 5 minus 1 over 5. So that's going to be minus 2 over square root of 5. So that's a minus sign that we pick up. But luckily, when we look at this guy over here, we have another minus sign. So those will cancel. So if we compare this calculation with the calculation that we had upstairs here, it's exactly identical, because the only places where it changes here will cancel in the end. So again, we have here minus 3j over 40. That was a lot of work, but now we're finally in a position to reap the fruits of our hard labor, which is to calculate the integral. The integral is going to be 2 pi j times the sum of all the residues that we've collected. So let's scroll back. For the origin, we had a residue of j over 10. So that's j over 10. And then for the other two guys, it's 2 times exactly the same. So this is going to be minus 3j over 20. Okay, so 2 pi. The j squared is going to be minus 1. And then also bringing that on the denominator 20. So it's minus 2 plus 3 divided by 20. So finally, it's pi over 10. That's a very long calculation, not difficult, but slightly arduous. And then we end up at the result that's pi over 10.